Hi everybody, and welcome to the last lecture of our Pneumonia-Classification project. In this notebook, you will learn how to use class activation maps to visualize image regions which are most important for the decision of a classifier. We will use a method called CAM, which was proposed by Bo-Lei Su and his colleagues in 2016 in the work Learning Deep Features for Discriminative Localization. As usual, I have already imported all necessary libraries. Starting with the magic command matplotlib notebook to get overall nicer plots, we use Torch for tensor manipulation, Torch Vision to get our ResNet 18, Transforms for normalization and resizing, PyTorch Lightning to create the model, NumPy for data loading, and last but not least Matplotlib to visualize some X-ray images and their corresponding class activation maps. At first, we should define some data loading methodology. As our goal is to load some validation data, we can copy the validation data set of the previous notebook. At first, we need to copy the load file function, followed by our validation transforms, and last but not least, the actual data set. Alright, now we are ready to start. The key idea of CAM is to multiply the output of the last convolutional layer with the weights of the subsequent fully connected layer. This produces a class activation map. To be able to do so, we need to access this particular output of our trained ResNet 18. Let us at first recap the ResNet architecture. To do so, we define a variable called temp_model, to which we assign the ResNet 18 implementation from torchvision.models. Now we should take a look at the model to find out how we can extract the output of the last convolutional layer. When scrolling through the model, we can see that the last convolutional layer is conv2 in layer 4. Alright, now we know that we have to extract the output of the second convolution in the second basic block of the fourth layer. In fact, we can also take the output of the subsequent batch norm layer. This makes life a little easier for us, as we will see later. In PyTorch, we can convert the network to a generator by using the children function. This means when calling tempModel.children, we obtain a generator allowing us to loop through all layers. This means that we can simply convert this generator to a list. As you can see above, we need to extract all elements up to the adaptive average pool 2D layer. This means that we simply collect all elements except the last two. When scrolling to the end of the network, we can see that this fulfills our goal of obtaining the output of batch norm 2D. The reason why we extracted the output of the last batch norm instead of the last convolution is that although we converted our network to a list, we still cannot access the individual layers within the sequential blocks. If you want to do that, you also have to convert these blocks into a list. This gets confusing very quickly. Last but not least, we can use torch.nn.sequential to convert the above statement back into a PyTorch model. In fact, and this is really important, you need to use the star operator before to unpack the list of layers into positional arguments. Perfect! As you can see, we have our PyTorch model back without the last two layers. Now we are ready to implement our adapted pneumonia model. We simply add an additional output to the forward function, which returns the feature map of the last convolutional layer. Note that as we threw away the adaptive global average pooling and fully connected layer, we need to manually add them back to the network. At first we define our Pneumonia model class, which inherits from the PyTorch Lightning module. Next we define the initialization function, which only accepts the self argument. We directly call the super constructor so we don't forget it. Now let's load the ResNet 18 and store it in a self.model variable. Of course, we need to change the input channel of the first convolutional layer from 3 to 1 again. Let us simply copy the values from above to define the parameters of the convolution. Don't forget to replace 3 by 1. Second to that, we also need to replace the out features of the fully connected layer. To do so, we can use torch.nn.linear, where the in features are 512 and the out feature is 1. Now it's time to extract the feature map. To do so, we simply copy the statement from above. Don't forget to replace temp model by self.model. Perfect! That's all we have to do in the initialization function. Our model definition is complete. To compute the prediction, let us define the forward function. At first, we extract the feature map and store it in a variable called feature map. To do so, we simply call self.featuremap on data. Next, we need to use adaptive average pooling as in the original model. We store the output of this layer in a variable called averagepool_output and now call torch.nn.functional.adaptive_avg_pool2d, which gets an input argument, in our case the feature map, and the desired output size, which is 1 times 1 in a ResNet. This function compresses the 7 times 7 times 512 feature map into a tensor of size 1 times 1 times 512 by taking the mean along the last axis. Before computing the output of the fully connected layer, we need to flatten our average pool output variable. Let us create another variable called avg_output_flattened and then use torch.flatten, where we pass average pool output. This creates a vector of shape 512. Now it's time to compute the prediction. We call self.model.fc, to which we pass our flattened output. Last but not least, we simply need to return the predicted value and the feature map. Our model definition is complete. Awesome! Now it's time to create an instance of our model and load the checkpoint. We use a variable called model, which stores everything, and then call Pneumonia-model.loadFromCheckpoint, to which we pass the path to our weights file. Let's use weights_3, and subsequently strict equals to false. The reason we need to pass this argument is that we changed the structure of our model by adding the self.featuremap variable. However, as the self.featuremap block did not exist when training the model, we didn't store explicit weights for this variable. Therefore, PyTorch will throw an error when trying to load the weights. When passing strict equals to false, it simply loads all weights it can match and ignores the rest. In our case, this is completely fine because we copy all weights from self.model. Please don't forget to set the model to evaluation mode. By adding the semicolon, we prevent PyTorch from printing the model summary. Now it's time to define the cam function. It accepts our model as the first argument and the X-ray image where we want to compute the class activation map on as the second one. Before doing anything else, we compute the prediction and extract the corresponding features. To do so, we can use with torch.no_grad to prevent PyTorch from storing the gradients, and then use pred, features equals to model, to which we pass the unsqueezed image. Alright, we computed the prediction and extracted the corresponding features. Our features are of shape 512 times 7 times 7. We can simplify the calculations by reshaping the three-dimensional feature tensor into a 512 times 49 tensor. To do so, we override our features variable and then call features.reshape, and now we pass a tuple containing the desired shape. In our case, it's 512 times 49. We now have a two-dimensional matrix. Next, we need to extract the weights of the fully connected layer. Let's define a variable called weight underscore params and access the model.fc parameters. In fact, we need to access at first model, which is the variable storing our pneumonia model. Next, we need to access the model defined in the initialization function of our pneumonia model, to finally access the fully connected layer. We can use the parameters function to obtain a generator containing all the weights. To allow simple access to those weights, we convert the generator into a list. Note that as we are interested in the weights and not the bias, we only access the first element within this list. Weight params now contains an array of 512 elements. We should directly remove the gradient information from the weights parameters to enable NumPy conversion. To do so, we simply access our weight params, remove the first batch axis and call .detag. Now we are ready to compute the class activation map. Instead of computing the scalar product between the weights and the features for each of the 49 elements, we simply compute the matrix multiplication. We write cam equals to torch.matmul, which stands for matrix multiplication, pass at first our weights and next the features. This matrix multiplication is possible because our weight variable contains an array of 512 elements and the feature matrix has a shape of 512 times 49. This yields a vector of 49 elements. Exactly the result we want. Last but not least, we simply reshape this array of 49 elements into our 7 times 7 matrix again and send it to the CPU. Now we are ready to return the class activation map and the prediction converted into a probability. Awesome! We just implemented the class activation map function. To visualize the class activation map, we can build a helper function called visualize. It accepts at first the X-ray image, next the class activation map, and finally the prediction. At first, we remove the channel dimension of the X-ray image. Next, we use transforms.functional.resize to resize the 7 times 7 class activation map to our original image size of 224 squared. Note that resize also expects a channel dimension. Therefore, we unsqueeze the channel dimension of the class activation map. Subsequently, we directly remove it again to make sure that matplotlib doesn't have any problems. Last but not least, we can create a 1 times 2 subplot figure where we visualize in the left plot the original X-ray image and in the right plot the combination of image and class activation map. To do so, we simply plot the original image at first and then lay the class activation map over it. We need to make sure that we pass the alpha argument to the imshow function to allow some transparency. Next to that, we use the chat color map because it yields a nicer class activation map. Additionally, let's also set the prediction as the corresponding figure title. We simply print the Boolean value returned by pred larger than 0.5. It evaluates to true if our model thinks that there is a pneumonia in this image, else it evaluates to false. Alright, now it's demo time. At first, we use our validation dataset to select a subject. Let's use index -6 because this is a particular nice X-ray image. As we don't need the label in this case, we can drop it. Next, we calculate the class activation map and corresponding prediction by calling the cam function. We pass our pneumonia model and the image we just loaded. Let's finally use our visualization function, to which we pass the original image, the class activation map and the computed prediction, to take a look at our first class activation map. Wow, this looks perfect. We can beautifully see how the somewhat foggy region of the X-ray image has a large impact on the prediction of the network. This happens in both the left and the right lung. We can also see that the outer parts of the lung, as an example, the shoulders or arms, don't have any influence at all. Our trained classifier did not just tell us that there is a pneumonia in this image, but also where we can find it. This is extremely helpful. Congratulations on making it to the end of our first medical imaging project. In the next project, we are going to create a detection network which is able to detect the heart in X-ray images. Thanks and see you soon.